Explain zone refining and column chromatography. Very interesting processes, both of them. Let's take a look. First, if you see zone refining is very extraordinary, and elements like silicon are used for ultra pure refining using zone refining. How is it done? See, you first have a silicon rod. Now, they have shown it horizontal here. We could also have it vertical. Say if you have a silicon rod, fine. And please note, we have to put them enclosed in a very inert chamber. We have a noble gas atmosphere so that there is no oxygen to mess around and react. And this metal, let's not call it metal, let us call it element. Like for example, silicon is not a metal, but still silicon is largely refined using zone refining because ultra pure silicon is needed for making computer chips, which you're using regularly, right? In mobile phones and every device virtually. So that silicon semiconductor is used, it is produced using zone refining. How is it done? See, a pure element rod is taken, and then you have a collar. No, not a collar like this. You have what you call something like a ring. Okay, the Lord of the Rings, whatever you might call it, like a ring like this. And this ring-like heater is there, which is capable of producing lots and lots of heat. So what happens is, as this rod is heated, it begins to melt. Inert atmosphere is there, so no oxidation is possible. Let's not forget that. And as this begins to melt, again, slowly this heater is taken down. Ding, 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 ding. Without any ding, ding noise. It is just taken down. So as heater moves down like this, what happens is, initially the heater was, say this is the rod. Heater was here. So this portion gets molten. Now the heater has moved down. The moment heater has moved down, now the lower portion begins to melt and the upper portion is no longer heated as strongly. So it begins to crystallize. It begins to solidify again. Now there is a fun concept, and that is, whenever a molten solution freezes, only the pure solvent tends to freeze and the solute does not tend to freeze along with solvent. This is a concept of nature. So when this molten silicon or molten element, whichever, or metal, again recrystallizes, only the pure metal or element wants to freeze or crystallize or solidify, and the impurity particles present in the liquid are not very keen to get solidified. Incidentally, there is also an opportunity, that now that this portion is solidifying, the lower portion, because the collar has moved down, the lower portion is now molten. So as the upper portion solidifies, the impurities which don't want to solidify along with the solid, they slowly migrate to the lower portion, which is already a liquid. Since it is already a liquid, it is possible for particles to move. So they migrate to the lower portion. And this continues. Now it again moves down. And now this middle portion has impurities of the top portion plus its own impurities. Now as this one is solidifying, the lower portion becomes liquid and they move down. And slowly the impurities migrate from top to bottom, or from one end to the other end. And once they reach the other end, this is cut off, thrown away, and you have a fairly pure rod of ultra pure element. This is a method which is called zone refining. Take a look. Column chromatography is a very interesting method. It is a method which is used for separating a mixture of substances which have very, very similar chemical properties. But still, if they are different, can they be separated using column chromatography? Yes. How do we do that? There are actually different phases. First point, where is it used? Not very different in chemical properties. They are similar in chemical properties. They are difficult to separate. Then we use column chromatography, right? What is the principle on which it is based? Different substances also, the chemical property is one property, but they have different tendencies to get adsorbed to a given substance. Say for example, we use something called as alumina or Al2O3. This is called stationary phase or immobile phase. And this stationary or immobile phase of Al2O3, what do? We take a glass tube. We fill the glass tube with small pellets of Al2O3. Why small pellets? Why not molten Al2O3 is frozen? We need some gaps between Al2O3 so that a different solution can pass. So what I've done, I have made a column. I'll show you the graph also, the figure also, in which I have filled up small pellets or some particles of aluminium oxide or Al2O3. These particles of alumina are not going to move. They will just stay where they are. And it is very important, like what is the criteria for choosing this stationary phase or immobile phase? The criteria is that this, number one, this phase should remain wherever it is. It should be inert, unreactive, and it should not dissolve in the solvent which we are going to pour down. Achha, are we going to pour down a solvent? Yes, we are going to pour down a solvent. A very good example is, say, if you want to separate, say, chlorophyll A from chlorophyll B and C. If you just take few green leaves, grind them, shake them with alcohol or benzene, and filter them, you will get a greenish solution. What happens is, this chlorophyll passes into the solution of benzene or ether or whatever, alcohol, whichever, some non-aqueous solvent which you are using. Great. Now, if you pour down this solution of chlorophyll down this column, you will observe something very interesting. What? As slowly the solvent passes. See, chlorophyll as such is a solid, so you have a solvent to dissolve it, and this solvent is sometimes called a mobile phase. It has nothing to do with mobile phones. It is just a mobile phase. It can be a gas, yes, it can be a liquid. It could also be a supercritical fluid. In our case, in the example of chlorophyll which I gave you, we are using a liquid. Liquid is much more easy to handle and generate. Otherwise, there are people who use gases, and there are people who use even supercritical fluids. If you want to be very stylish, you can do that. And as this liquid goes down on account of gravity, it is pulled down by earth. And since it has different solutes, more than one solutes dissolved in it, and these are the solutes you want to separate. So as it slowly passes through, it drips through this column, you find that, say, chlorophyll A, chlorophyll B, chlorophyll C, they have different tendencies to get adsorbed on alumina, or they have different tendencies to get stuck on alumina. Okay, so what happens is that they are moving through the stationary phase at different rates. They are moving through the stationary phase at different rates. So the one which moves slowly is left behind. The ones which move more quickly goes ahead. You find you would get, say, you get 2 bands, that means there were 2 different solutes. If you get 3 bands, you get 3 different solutes, and you can separate them. Since chlorophyll gets separated as 3 different bands, you call them chlorophyll A, chlorophyll B, chlorophyll C. Now you might say that I want to recover the chemical also. Is that possible? Yes, that is very much possible. How is that possible? Now say you have chlorophyll A, B and C. Once all this has passed through, now you start adding pure solvent. Say pure, if alcohol was the solvent or ether was the solvent, you start pouring pure ether. As pure ether goes down, it dissolves, maybe this, but it comes down slightly. This also comes down, but since this has minimum tendency to get stuck on alumina, it gets washed out and it can be washed down more cleanly. So later on, after some time, slowly, as you keep on pouring more and more ether or solvent, more and more, slowly each of them gets washed down, but at different rates. Most easily this can be washed out, so you can separately collect chlorophyll A, and then you can see this band slowly vanishing because it has been washed out. Other bands are moving down. Then in a separate bottle you can recover chlorophyll B, and in a separate bottle you can recover chlorophyll C. A very beautiful, very simple and very successful method of column chromatography to separate components which are chemically very similar, which are otherwise very difficult to separate. But if they have different tendencies to undergo adsorption, and mostly substances have different tendencies to undergo absorption, you can separate them using column chromatography. This is the method.